Hello, in this video we will have a fairly short session talking about pumping wells and how they're represented in Anaqsim. There are basically two kinds, discharge specified and head specified, and they can span just a single domain or in a multi-level model, multiple domains. We'll talk about all of those options. And we'll talk about what we mean by the well radius when you specify, for example, the head at the well radius. And we'll look at some of the outputs that can be generated. So for a discharge specified pumping well, you name the discharge and it will be negative if you're extracting water out of the aquifer and positive if you're injecting water back into the aquifer. That's just a convention that's adopted here. And the other kind are head specified wells where you specify the head at the well radius. And generally that is the radius to the formation outside of the well casing or outside of the very conductive sand backfill around the well screen. And for a head specified well, Anaqsim solves for the discharge. And analytic element method is excellent at representing pumping wells, much better than numerical methods like finite differences or finite elements, because the analytic solution has the proper logarithmic shape to the drawdown curve, which numerical methods generally lack. They are assuming linear variation or something like that. If you have a discharge specified well in a single domain, there are no equations generated because you know the unknown strength, which is the discharge of the well. When you have a multi-level discharge specified well, there are some equations being generated. Let's say it spans 3 domains vertically, your well screen. If you have a discharge specified well, the sum total of the discharges coming to the well in all 3 levels or 3 domains has to sum up to the specified discharge. So that's one equation. And then the other constraint is that you want the head at the well radius to be the same in all the domains spanned. And if you have m levels spanned, that means m minus 1 equations. So you end up in total with m equations for m levels spanned. One interesting application is this third bullet here. If you have an abandoned well that spans multiple levels in an aquifer system, you can use the multi-level discharge specified well with a discharge of 0 to simulate the vertical flow that will occur between levels that are in contact with the screen. And I know of a few case studies, one in a basin in Australia where there were all kinds of abandoned gas wells where they were used in this way. It's quite handy. Head specified wells are quite handy to answer the question of how much discharge do we need in order to create a certain head at the well radius. And this could be extraction and good for, say, a dewatering analysis, or it could be an injection situation where you want to know, how much water can we inject into a well before it breaks out at the surface or something like that. When you want a head specified well in a multi-layer situation where the well screen spans multiple layers, you have two options. You can use separate head specified wells in each of the levels that the screen spans, and you put the well coordinates at the exact same x, y location, so they'll be right above one another, and Anaqsim will solve for the discharge in each level. Another way would be to use both a head specified well in one level and a discharge specified well multi-domain that spans all the levels involved, but set the discharge of that to 0. Then the total discharge of the well across all the levels spanned will be reported in the output for that one head specified well. So either of those options gets you to the same place. The well radius is something that you input for a pumping well, and the assumption is that at the well radius, the head is equal to the head in the well bore itself. And that could be just the outside of the well screen, like where my cursor is right here. If you've basically installed a well and allowed the formation to collapse around the screen, or it might be a bit further out if you've drilled a larger diameter hole and then backfilled around the screen with a very permeable filter pack that is much more permeable than the formation itself out here. In that case, you would use the radius out to the outside of the filter pack. So that's a bit of a judgment call and is based on the permeability of the filter pack relative to the formation itself. Here are the outputs that you can generate for a pumping well. For a discharge specified well, you can output the head at the well screen. And you can do that for a steady state model or at each time step in a transient model. Anaqsim can also generate automatically plots of this versus time, like shown here on the left. This is a discharge specified well that's turning on for the first 50 days and then shutting off beyond that. And we've got a plot of head versus time. Apparently it's an injecting well, head rose, and then after shutting the well off, it dropped. So for a head specified well, you can output the discharge, again, at every time step in a transient model or the one number for a steady model. And you can generate plots like this one, which is a transient model with 3 time periods. And for the first time period, there is a specified head, and it starts off extracting something like 1,200 units. Perhaps this is cubic feet per day or something like that. And over time during that period, the discharge tapers off because that's what you'd expect. If you have a fixed head, you're going to generate a lot of discharge in the first minutes and then have it taper off with time. The middle time period, over this span from 10 to 12, the well is off, and that's something you can do in a transient model. You can turn a head specified pumping well off for time periods if you want. And in this one, that well turned on again with a even lower specified head, so larger discharges are required in the third time period here. Notice that it's kind of a stair-step affair rather than looking like a smooth curve, and that's because in the model, in the actual mathematical model, the discharge is assumed constant for the duration of a time step. And these are finite difference time steps in the transient simulation. So it jumps from one step to another what the required discharge is to create the specified head at the end of the step.